Okay, so in this video we're going to talk some more about Hooke's law, and then we're going to talk about the bouncy motion of a spring, and hopefully we'll get through that in, well, we're not going to get through it in 10 minutes. It's going to take another video at least. Okay, so here I've got a spring scale, and if you think about it, the whole concept of a spring scale is based off of Hooke's law, because you've got these little marks on here, 0, 1, 2, 3, 4, 5. Now I've got it set up so that it reads 0 if it's vertically, and it's not vertical right now. But so they're evenly spaced. Well, they're evenly spaced because if I apply 1 Newton of force, it stretches, well, how far apart is that? 1 centimeter. So if I apply 1 Newton of force, it stretches 1 centimeter. If I apply 2 newtons of force, it goes 2 centimeters. 3 newtons of force goes 3 centimeters. And just like that. And so this whole thing, the behavior of this spring scale is based on the idea that you can make a graph where as you apply more force, as I apply more force down here, the length of the spring increases like that, or the length of the stretch increases like that. Okay, so I want to look, and I want to sort of hit this from a different perspective, and what I want to do is I could give you the equation, and ultimately, like, you can probably see the equation and you know what the equation is, but I'd sort of like to come at it from a different way. From this data here, I said that 200 grams corresponded to a time for 10 bounces of 11.16 seconds. And 100 grams corresponded to 8.0 seconds. Well, let's look at ratios, because ratios are always really, really, really important. So if I say 2 to 1 is the same as 11.16 to 8. But let's go 2 to 1 is the same as, what is 11.16 divided by 8? It's 1.395. Now that's a little bit far off from what I wanted to get, but in an ideal universe, which we're not living in, I would have gotten 1.41. And I want you to think about why I said you should get 1.41. That's sort of an approximately sign. Why did I get 1.41? Or why should I have gotten 1.41? Well, the reason why is that this is the square root of 2. So what I really wanted to say is that if my masses were in the ratio of 2 to 1, my times, or I'm going to call them periods, are in the ratio of square root of 2 to 1. So now that suggests that if I had an equation that I would say that my time is somehow proportional is equal to some sort of constant times the square root of mass. Well, and maybe some other stuff in there too, you know, and maybe some other stuff that we don't really know yet. So we're building up an equation, and I don't really know what's in there. So I've got a lot of unknowns, so this is all sort of hazy stuff that we have to fill in. But I know that the time is somehow related to the square root of the mass, because if I double the time, or if I double the mass, if I take the square root of that, that'll give me the time. I know that's clear as mud. Okay, so then I went back and I said the stiff spring was 7.54 seconds. So I'm going to say stiff to loose, the times were 7.54 to 11.16 for 200 grams. Well, what do we mean by stiff and loose? Well, we now have numbers that we can apply with our stiff and loose. We said our stiff was 14.7 newtons per meter, and my loose was 6.5 newtons per meter. And then we have 7.54 seconds to 11.16 seconds. So again, doing it one-to-one, we have 14.7 divided by 6.5 is 2.26 to 1. And then this is 7.54 divided by 11.16, and I get 0.6756. So 0.67, I'll call it 0.676 to 1. Okay. Well, what can be the connection here? Well, one thing that I want to look at is, I think that these are inversely related, that as the spring constant goes up, the time goes down. It might help me if I actually sort of do it this way. If I do 1 to 11.16 divided by 7.54, I get 1.48. And I go, wait a second here. I said that the square root of 2 was 1.41. I wonder what the square root of I wonder what this squared is. I wonder what 1.48 squared is. The answer is 2.2, 2.19. So again, I'm just kind of going through this fast, but what we come up with is, if this is K, K1 to K2 is proportional to what I'm going to come up with here, and I'm going through this really fast, I know. This is where we need to come to class and have discussion. I'm going to say that my time is somehow, with all this other junk, is going to be proportional to 1 over K. So now, in the last few seconds of this video, I have time is proportional to some junk, square root of m over square root of k. That's that video.